Hi, this video will cover section 2.6, rational functions, and the objectives that are listed here. We have find the domains of rational functions, find the vertical and horizontal asymptotes of the graphs, sketch the graphs of rational functions, also sketch the graphs of rational functions that have a slant asymptote, and finally, we'll solve a problem with some real-life application. So let's get started. And the definition of a rational function is the quotient of two polynomial functions. So what we mean by that is the quotient is also the ratio. So rational derived from an extension of the word ratio. And so it's going to be the ratio of two polynomial functions. And so in chapter 2, most of it is about polynomial functions. So now we're going to have two polynomials being divided, and that's what will make a rational function. So we have here both n of x and d of x are polynomials. And also we have to be very careful that the denominator, and actually that's why they're using those letters, n for numerator and d for denominator. So we have to be very careful that the denominator is not the zero polynomial, meaning a function or a polynomial that equals to 0. And that is because if that was the case, then we wouldn't have a defined function. We cannot divide by 0. Remember, it's okay to have 0 on the numerator, but it's not okay to have the 0 in the denominator. So that will be undefined. So same thing with functions. The denominator cannot be the 0 polynomial. So in general, we have that the domain of a rational function of x includes all the numbers, all the real numbers, except those x values that make the denominator equal 0. So that's how we're going to be finding that. And we did a little bit of this in chapter 1 when we introduced functions and the concepts of domain and range. But we're going to practice more with this ones, with rational, we'll do more examples of rational functions. Okay, so for the domain, we're going to have to find those numbers, those x values that will cause that denominator be 0. And so for that, let's go ahead and start with the parent function. And we have that f of x is equal to 1 over x. And just to remind you how that looks like, I'm not sure if you actually got to look at the graph. I think so. And it will be something like two hyperbolas rotated, and actually they do not touch the x or the y axis. And what we do call those with respect to this function will be asymptotes, which we're going to learn how to find as well. So the reason I'm drawing the dashed line is because that is not part of the function. In fact, it's the only x value. So the vertical asymptote is the equation. The equation is x equals to a number because it's x equals 0. That's the equation of the vertical line. So that same vertical asymptote is the number that we exclude from the domain, because for that function, f of 0 is undefined since it will be 1 over 0. So what we're going to be doing is always taking the denominator, the expression, and we will be creating an inequality that will say that denominator cannot equal to 0. And so because of that, the domain will be defined as all real numbers except for 0. So in interval notation, that goes from negative infinity to 0. We exclude 0 with the parentheses. We use the symbol for union, and then from 0 to positive infinity. Okay, now that same value, 0, is the same as our vertical asymptote, but with the vertical asymptote, we're saying that in fact equals 0. Now we also have another one called the horizontal asymptote, so we will also learn how to find those. And in this case, the horizontal asymptote is the y-axis, so the equation for it is y equals to 0, and that is horizontal asymptote. And that is because there's no output that we will ever get that will say that will be equal to 0. So there's no f of x that will equal 0. And so for that reason, the range, which is the y values, we could say y will not equal 0, or if we write that as in interval notation, that will be also from negative infinity to 0, union 0 to infinity, because we're excluding y equals to 0, so that's why we use the parentheses. So that would be the horizontal asymptote. And that is the graph. Now the graph, we could also see that it is decreasing. On the left side, you could see very clearly it is, if we read it from left to right like we should, it is decreasing, and it is also decreasing on the right side of the y-axis. We could also see how as the x values get larger, the y values approach zero. And so that's also another good explanation for having that horizontal asymptote at 0. So if I was to extend this function, it will get closer and closer to the x axis, but it will never touch it. If we look at it on this left side, same thing. So we could make a similar statement that as x gets smaller, y approaches getting closer and closer 0, the value of the horizontal asymptote. Okay, now with our vertical asymptote, that one, we could make two types of statements that as our x value of the graph gets closer to 0, as x approaches 0, from, remember this is the value, the origin is that point with the coordinates 0, 0. So that's what we say, as x approaches 0 from the right side of the y-axis, or from the right side of the vertical line, f of x, or the y value, approaches infinity, or positive infinity. And if we look at what's happening on the left side of the function, as we approach the x value of 0 from the left, so as x approaches 0 from left, the y values are getting smaller and smaller if you follow the behavior of this graph. So in that case, we said that f of x or y approaches negative infinity. And so we're not going to be writing sentences like that all the time. We are going to introduce some notation for this, and it's very important, and especially if you are going to take calculus, because the first topic is called limits, and so understanding asymptotes is actually quite important. Okay, so I'm going to try to select the statement I wrote here. I hope I can get the whole thing. Okay, maybe. And that goes right here. Now let's see, what are we missing? Okay, I'm just gonna rewrite it. Okay, so I decided to just introduce arrow notation right now. So we're gonna say, instead of writing as x approaches, oops, that looks very dark. As x approaches 0 from the left, it's gonna be here. As x approaches 0 from the left, so the arrow is indicating that it's getting closer, and the negative, that looks like an exponent, it means from the left. Then on the bottom part, we have f of x or y approaches negative infinity, and so that will be this notation. Or of course we could also say f of x approaches 0. All right, now as you can see here with the y values, the x values, so we have -1. So imagine you have your number line, here's -1, and then 0 is over here. So -0.5 will be here. Which is closer to 0, and then -0.1 is even closer to 0. And then -0.01 is even closer to 0, and -0.001 is even closer to 0. So they're getting closer, they're approaching 0, but they cannot be 0. Remember, x equals 0 is excluded from the domain, meaning we cannot substitute x into the function. Okay, now let's look at what's happening with the second table. Oh, well, before I do that, notice how the closer we get to 0, the y values keep getting smaller. And I say smaller because they're getting more negative. Like -1000 is way smaller than -10, right? Even though with positives is the opposite. So here we say that the function is approaching negative infinity, is going down to negative infinity, decreasing in value. Okay, now the second table. So we have here as the numbers approach 0 from the right side. So we have number 1, then if we do that on the number line again, so we have 1 here, here is 0. So we're approaching from the right. We have 0.5, and then we have 0.1, and then we have 0.01, and then we have 0.001. So it's closer and closer. So the x values are approaching 0 from the right side. So we use this notation: as x approaches 0 from the right side. So we indicate that with the plus sign of the size of an exponent. And then what happens is the function is approaching, and as you can see what's happening here, they're getting larger. So we go from 1 to 2 to 10 to 100 to 1,000. So the closer we get to 0, the larger the number we will get from the right side. So we say that the function is approaching infinity. And so that is the same thing that I wrote over here on the previous slide. So we had as x approaches 0 from the right, that will be this notation, as x approaches 0 from the right, and then we have f of x or y, whatever you want to call it, is approaching positive infinity. And so that will be this part right here. Okay, now the other two statements that we made were that if x gets larger, the y values approach 0. And we also say as x gets smaller, the y values approach 0. So let's see how that will look within our notation. So we have here as x approaches 0 from the left. Oh, this is the one that we already wrote down. So 0 from the left, that will be here. The function value approaches negative infinity, right? And we can also say decreases without bound. And then the other one that we did here will be as x approaches 0 from the right, the function approaches infinity, right? It goes up to infinity. This one goes to negative infinity. Okay, and we could also say f of x increases without bound. So without bound, that's why we use the concept of infinity or negative infinity. And here on this next one, okay, yeah, so it doesn't have that. So let me just show you how the other two will look with arrow notation, since we don't have them here. So we're going to say that right here, as x gets larger, so we could say as x approaches infinity, f of x approaches 0, right there. And then for the other one here, as x gets smaller, but with arrow notation, we will say approaches negative infinity, the function value approaches 0. And that's why we have that horizontal asymptote from those two statements. The vertical asymptote, what color should I use? Let's use this. Will be here. And it comes from the fact that we have the opposite behavior, one going to negative infinity, the other one going to infinity. So instead of meeting each other, they go in opposite directions. All right, so we have a summary of that on this table. So we have again here vertical asymptote, which I highlighted with yellow on our previous graph. And that, because it's a vertical line, must be x equals to a number. And that happens when, remember we were saying, and here if we use it with a, it will be something like as x approaches a from the, let's use from the right, just to keep it like the parent function, f of x approaches infinity. And then that will be this statement here. And then the other one will be as x, and remember a is just a real number, approaches a from the left, f of x approaches negative infinity. And we get our horizontal asymptote from the other two statements that we made. Since it is a horizontal line, it needs to be y equals to a number. In this case, we're using the number b, or the letter b, to denote a number, to generalize it. And so for this one, we made the two statements, the first one being as x approaches infinity, f of x approaches 0. That was the number that we used. In this case, we will call it b, just to generalize it. And then the other one was as x approaches negative infinity, meaning getting smaller, f of x, the function value, approaches b again. With our example, we used the number 0 because it was the parent function, but with this one, we use the letters A and B. Okay, so let's move on from here, and we have here some examples of vertical and horizontal asymptotes. So for example, here this function has a vertical asymptote there because x cannot be a -1. That will be the exclusion from the domain. So here it's the vertical asymptote. And then we have the horizontal asymptote, which is here the line y equals 2 is horizontal. And so that's what it is. So we will learn how to find those shortly. Then the next graph has no vertical asymptote. You guys notice? No, and that is fine. So, some might not have it. And that is actually, it comes from the fact that the domain of this function is all real numbers, and you might think, well, isn't there a number that will cause the denominator equal to 0? The answer is no, because this polynomial here, if we try to solve for it, to find the x value that will cause the whole expression to equal to 0, it will have no real solution. If you recall from complex numbers, we cannot take the square root of negative, and so we use the concept of I. But if the solution to the expression is in imaginary numbers, then that means that there's no exclusion in the set of real numbers, therefore there's no vertical asymptote. So that's fine. And then for the horizontal asymptote, we do have here the line y equals 0. Now, your calculator may not graph the asymptotes, so that's why it's important that you learn how to find them numerically or algebraically. And then we have here the vertical asymptote, 1, x equals 1. And so is this one here. I'm going to highlight it. And then we have the horizontal asymptote at y equals 0. So you can see here that if we were to find a domain, we will take the denominator and equal it to 0, or actually does not equal 0 to find a domain. So first thing will be to take the square root on both sides, and then that will eliminate the square. So x minus 1 cannot equal the square root of 0, which is 0. And then this will be x does not equal 0 plus 1, or just simply x cannot equal 1. And that will be the exclusion from the domain is the same as the vertical asymptote that you see here. All right, let's see what else. Okay. So here we have a summary of the 3 types of rational functions. So the 3 types will be defined based on the degree of the polynomial that is on top, the numerator, and the degree of the polynomial that is on the bottom, the denominator. So we're going to use the letter n right here. Remember, this is the definition of the polynomial. We saw that with since section 2.1, I believe. So right here we have the leading term. N is considered to be the biggest exponent, so the degree of this one is n. So degree n. And the leading coefficient is going to be a sub n. That will be a number. The subscript is just a label to tell us that's the coefficient of the leading term, which is xn. So we have leading coefficient is a sub n. Okay, so that is what we're going to use to compare to the degree of the denominator, which is m, and the leading coefficient is b sub m. To denote, the subscript is to denote that it goes with x to the power m, the biggest exponent. Okay, so that's what we're going to be comparing and in using. Okay, so also it's important to notice that the two polynomials have no common factors, meaning that they are already reduced, which we are going to review a little bit of. And so number one says the graph of f, which is the rational function, has vertical asymptotes at the zeros of d of x. And so remember how we calculate the domain and we use the whatever's in the denominator cannot equal 0? Well, with vertical asymptotes, we take the denominator and we equal it to 0. And so we find the x values, and we could have more than one vertical asymptote, just so you know. The x values that will make that denominator be equal to 0. So that's why it says here we're looking for the zeros. All right. And remember, if that has no real zeros, then there are no vertical asymptotes, like the example of the graph that we saw. Number two says the graph of f has one or no horizontal asymptote determined by comparing the degrees of n of x and d of x. So that is very important too. So this is for vertical asymptotes. Now the other three statements are specifically to horizontal asymptotes. So we have three cases that we have one or no horizontal asymptote. And I know, okay, that sounds like two cases, but we're going to break them down in three types. So type A is when the degree, when n, you can see here, is less than m. So we're saying that the degree of the denominator is greater, right? So I like to refer to this type of functions as bottom heavy. In this case, m is greater, the degree of the polynomial on the bottom, so bottom heavy. Then our next case will be, well, let's look at the third one, is easier. The third case is when n is greater than m. So in this case, the numerator, the polynomial in the numerator, it's greater. So n is greater. So in that case, we're going to call it top heavy. Then our second case, B, is whenever n is equal to m. So that means that they have the same degree. Okay. So whenever, let's start from the third case. So whenever the numerator, the degree of the numerator is bigger, we're going to have no horizontal asymptote. And instead of that, we're going to have this thing called slant asymptote. And we are going to look at those at the end of this section. Okay, so whenever the degree of the denominator is the bigger one, then our horizontal asymptote by default is going to be the line y equals 0, or also known as the x-axis. That will be the horizontal asymptote. And then when the degrees are equal, numerator and denominator, then that's when we're going to use the ratio of the leading coefficients as the horizontal asymptote. So that will be our coefficient from the numerator that we have here, a sub n, divided by the coefficient of the denominator, b sub n, m. And recall that those are numbers, so we're going to get y equals to a number, so that's why it's also a horizontal asymptote. So bottom heavy, y equals 0 by default, unless there's like a vertical shift. And then the ratio of the leading coefficients when they have same degree, and then when they're top heavy, no horizontal asymptote. So make sure you do have this handy when you take your exam 2. Okay. And yes, it should go on your formula sheet. Okay, example 2. So we're gonna do, we're gonna be finding all vertical and horizontal asymptotes of the graph of each rational function. We're not gonna graph them, we're just gonna find the vertical and horizontal asymptotes. So let's get started. First, let's work on that vertical asymptote. So you know it's gonna be x equals to a number. We need to find that number. Or we might have more than one. In this case, we will. So we take the denominator, x squared minus 1 equals 0. And then we solve for x, so we could say x squared is equal to positive 1. And then if we take the square roots on both sides, we will get that x is equal to positive and negative 1. So we're going to have positive 1 and negative 1 as the vertical asymptotes. Now for the horizontal, we are going to classify this. So let's see if it's top heavy, bottom heavy, or same degree. So you could see right away how the degrees here, we have a 2 and a 2. So we could say that they are of same degree type of rational functions. They're both of degree 2. So then we're going to use the ratio of the leading coefficients. And so those leading coefficients in this case will be 2 over, and here the leading coefficient is a 1. So 2 over 1. So then the horizontal asymptote is the line y equals to 1. Okay, next example. Same thing, vertical and horizontal. So for vertical asymptote, I'm going to just start using VA. So we take the denominator that we see here, x squared minus x minus 6 is equal to 0. So I'm going to solve this one by factoring, and we will have the factors x plus minus, and the numbers that we need will be 3 and 2, because positive 2 times negative 3 is negative 6, and then 2 minus 3 is negative 1. So then we take each factor, equal it to 0. Stop it, Tommy. X minus 3 is equal to 0. And then we solve for x. X is equal to negative 2. X is equal to 3. And yep, those will be the 2 vertical asymptotes. Let's find the horizontal one. So HA. And so for that, we have, again, same degree rational function. So that's going to be the coefficients of the leading coefficients. So that will be 1 over 1, which equals to 1. So the horizontal asymptote is the line y equals 1. Okay, so let's find some, let's go over some steps on how to graph rational functions. And so we have the very first step needs to be to simplify the function if possible. Then you will find, I will probably say that finding the asymptotes is probably better. The vertical asymptotes by setting the denominator equal to 0. And then I will probably go ahead and find the horizontal ones. Let me see. Finding the horizontal asymptotes. Those are very useful. Then from there, sorry, I will probably move on to steps 2 and 3 and find the y-intercept. And remember, we do that by letting x equal 0, just like we do with any other function. And then we find the y coordinate. Then for number 3, find the zeros of the numerator. And remember, those are also the x-intercepts if they're real numbers. And that will be by solving the numerator. And that's how you find the zeros, the solutions, the x-intercepts, if they're real numbers, of course. And then also finding the vertical asymptote tells you what the domain is. So that is also pretty useful. But remember, the domain you use the does not equal or exclude the numbers that you find for the vertical asymptotes. Then you start plotting your points in between 1 point between and 1 point beyond the x-intercept. So once you find that, the x-intercepts, you want to know what's happening between those, a point on the x-axis and then another point. Like you want to see if it's gonna, the behavior will be going this way perhaps, or if the behavior might go that way. So you want to see what's happening. And then so you plot points, and then you use smooth curves to complete the graph. So make sure that they're not straight lines. They have to be curvy. And you draw those between and beyond the vertical asymptotes. Horizontal asymptotes, sometimes they get cross, but vertical asymptotes, they do not. Okay, so we're gonna sketch the graph of this rational function. So first of all, let's see what type of rational function we have. You can see the degree of the top is 0 because we just have a constant term. So n equals to 0, and then the degree of the bottom, which is m, it's a 1. So you could see the degree of the bottom is bigger, so we can consider this one bottom heavy. And so that helps me locate the horizontal asymptote pretty easy, and that's because it's by default y equals 0 if you have a bottom heavy rational function. Now let's find the vertical asymptote, and so for that we take the denominator, which is x minus 2, And we could say that equals to 0. So we solve for x. So it will be x equals to positive 2. So the vertical asymptote is the vertical line, x equals 2. For the, what else? The domain. So the domain will be similar, taking that value, but we're going to say does not equal 2. So x must be excluded. So remember, an interval is negative infinity to 2, union 2 to infinity. Stop it, Tommy. So let's go ahead and find the x and the y-intercept now. So for the x-intercept, if you look at your list, we only need the numerator. Set the numerator equal to 0. And I'm going to erase this x to the power 0. So if we say, that's going to be a little weird. Let me do it the long way. So if we, to find the x-intercept, we will have to let y equals 0, right? Or g of x equals 0. So we will have the equation 0 equals 3 over x minus 2. Now, what I will do here is first get this denominator out of there. So you move it across the equal sign. But because you are, multiplying by 0, that whole side turns to 0. So 0 equals 3. And because this is not true, then we say does not exist. I think that's what WebAssign will have you do. DNE does not exist. For the y-intercept, on the other hand, we will be finding g of 0. We let x equal 0. So this x here turns into a 0. So that means we substitute a 0 into the equation. 3 over x is 0. And then we have a minus 2. So here we're going to get the number 3 over negative 2. So that means that the y-intercept is the point 0 for x by default, and then negative 3/2. So let's go ahead and type what we have, plot the points that we have. So let's start with the horizontal asymptote. So let's see. The horizontal asymptote will be the y equals 0, this line. So it's going to look like that. And then the vertical asymptote is going to be this line, the x equals to 2. And when you graph this on WebAssign, make sure that you make your asymptotes to be dash lines, not solid. Because if you don't make them, if you make them solid, the program will count them as wrong. Okay, now let's go ahead and find and plot the y-intercept. So that is the point 0, comma, negative 3/2. So that is like negative 1.5. So 0 for x and then negative 3/2. So that would be like right. Actually, I'm gonna just zoom in. So it will be like right there. Oh. There we go. And so now what we want to know is what's happening with the graph. And so we could choose another point. For example, we can make x equal to 1. So we say let's find g of 1, and it will be 3 over 1 minus 2, which will be 3 over negative 2. Okay, I don't think that is correct. Oh, okay, my bad. So 1 minus 2 is negative 1. There we go. That makes more sense. And so this turns into negative 3. So let's go ahead and plot that point, 1 comma negative 3. And so that will be 1 comma negative 3. I'm going to zoom in again. So 1 for x, and then negative 3. So we'll be here. Okay, interesting. Now let's see what will happen if we find g of negative 2. And so that will be 3 over negative 2 minus 2. And so that will be 3 over negative 4. So we could also say negative 3/4. So that's like negative 0.75. So we will plot the point negative 2 comma negative 0.75 or negative 3/4. So let's see. That will be negative 2 for the x, and then almost getting to the 1, like a quarter away from the 1, from the negative 1 for the y. So you could start seeing how the graph will look like, and you could see here I will connect the points like that, and then just, make sure that I do not touch the asymptotes. Now for the other side, we could find g of 3. Let's see. G of 3 will be 3 over 1 minus 2. So g of 3 will be equal to 3 over negative 1, which will be negative 3. So that's an easy point to plot. It will be 3 comma negative 3. Wait a second. I don't think I did this right. What am I doing? I did not substitute correctly. Sorry, so it's 3. The equation is x minus 2 on the bottom, so it should be 3 minus 2. That's what it should be. So it's 3 divided by 1, which is equal to positive 3. So the point that we need to plot is 3 comma positive 3. That makes more sense. So 3 and comma 3. So that will be here. So here we go. And let's find g of g of 5. Let's find that one. So g of 5 will be 3 over 5 minus 2. So g of 5 will be 3 over 3, which is 1. So we will plot the point 5 comma 1, and that will be here. Okay, so I'm gonna go ahead and connect the points. maybe I should find g of 4. So g of 4 is going to be 3 divided by 4 minus 2, which will be 3 over 2. Okay, so that's g of 4, and that will be the point 4 comma 3 halves. So that's going to be here. Okay, now we can connect them. That looks a lot better. And then extend the lines so that they do not touch the vertical or the horizontal asymptote. And I mean, of course, you're welcome to use technology to verify your answer. So we have here slant asymptotes. So remember, when you have a function that is top heavy, that is because they do not have, that's because top heavy implies that there is no horizontal asymptote. So instead, they may or may not have a slant asymptote or oblique asymptote. So that's an example of a slant asymptote. And just like we study in chapter 1, those lines are going to be functions, and the equation of those will be y equals to something. Now, if we had just y equals to a number, we will be calling it a horizontal asymptote because it will be a horizontal line. But in this case, we do have x and y-intercept, or we might just have x with to the degree 1. The exponent will be a 1, and the coefficient could be whatever. And the y-intercept could also be anything. They could be leaning to the right, leaning to the left. So that's how they look like. And here you could see that there is a vertical asymptote as well, but no horizontal asymptote. And you could see how that equation is top heavy. The degree of the numerator is bigger than the denominator because the denominator is a 1. And so, yeah, we have that. So let's see how we will find one. And so what we're going to do is use, we could use synthetic division or long division. So if we do that, we will be simplifying this one. Remember, that was the very first step to graph them. And that is because sometimes, that will change completely the way that we graph it. So if we take x squared minus x and divide that by x plus 1, we divide x squared by x, and that gives me x. Then I multiply x times x is x squared, and then x times 1 is positive x. So then I have to change the signs because I'm subtracting, so that goes to negative, and this one also goes to negative. Then I have to combine like terms vertically. The first two cancel. Here I have negative 2x. And then I don't have any more terms, so I'm just going to assume I have a constant term of a 0. And then I divide again, negative 2x divided by x. So that will be minus 2. And then we multiply. Negative 2 times x is negative 2x. And then negative 2 times positive 1 is negative 2. So then I have to subtract, so I change the signs to positive, positive. And here you could see those two cancel, and the remainder, it happens to be positive 2. So just like we did with the division algorithm, we're going to rewrite that function to look like that by using the quotient, which is there, and the quotient happens to be the slant asymptote. Now the remainder, which is here, we still have to write it here, and then just like a mixed fraction, like if we had 27 is divided by 5, it will be 5 plus 2/5. So similar like to that. And so we still include the denominator of that function or the divisor there, just like the 5 will be there if we change that improper fraction to a mixed fraction. So there you have it, x minus 2. So if we consider the line, the slant asymptote, y equals x minus 2, we know that the y-intercept is equal to 0, negative 2. So I'm going to start by finding that, and I'm going to use an open circle because that's not a real point on the graph. In fact, like the graph can't touch it. So 0, negative 2 will be here. Like that. And then the slope of this function is, of the slant asymptote, I should say, it is equal to 1 because it's the coefficient of the x. So the slope is 1. So that implies that I will be going from that y-intercept 1 up, 1 to the right. So 1 up, 1 to the right. And I'm just going to keep using open circles. 1 up, 1 to the right. 1 up, 1 to the right, or 1 down, 1 to the left, 1 down, 1 to the left. As you see, they will all be on the same line. So, I mean, I could just extend it a little more in both directions. Now, when you graph this on WebAssign, you will use the function to make a dash line. And for questions about graphing, please direct those to the tutors. They are way better at that. Okay, so this dash line, you don't need to put open circles. I just did that. Oh. Okay. Then we should find the vertical asymptote. And so that one is going to come from here. And so we're going to take, for the vertical asymptote, we take the x plus 1, equal it to 0, and then x is equal to negative 1. So that is the vertical asymptote. And that will be here at negative 1. Also, I'll be doing a dash line. And then we just need to see what's happening with this graph. So, for example, if we substitute 0 into the equation, let's see what will happen. If I substitute 0 here, I will just get 0 over 1, which will be 0. So I'm going to be using the reduced form of the equation and finding f of 0. So f of 0 is equal to 0 minus 2. And then I have this part as well. So it is 2 over 0 plus 1. So if you notice, I'm substituting a 0 here and here. So then I will get negative 2. 0 minus 2 is just negative 2. Plus 2 over 1, which is equal to negative 2 plus 2. And that happens to be 0. So that's very nice because this is giving us the point 0, 0, which is at the origin, and therefore it is the x and the y-intercept as well. So we have the point here. at the origin, 0, 0. Now, just for time convenience, I'm just going to go ahead and draw it. So like that. And, you know, if you don't want to test points, I mean, you could always type them in your calculator, do them by hand, or, you know, you can graph it with your calculator and then get the table. So this will be another graph. So let's see. First step is to simplify. So what I'm going to do is I'm going to factor the numerator, and that will be x plus minus 2 and 1. The 2 goes here, the 1 goes here. Now, you could see, oh no, this one does not. Oh, I wish this was a plus. Let's do that. Let's make that a plus. So I'm changing the problem so it has a plus. And I have a reason for that. So this is very important too. So for example, if you happen to find two factors that they're in common, you could cancel them out, right? Because they equal to 1. So then you are just left with one factor, and it is x minus 2. Now, this may look like a linear function, but it's the result of simplifying a rational function. And so what happens here is we could factor it pretty easy, but we need to figure out some things. Are we going to have a vertical asymptote? No. Why? Because we were able to reduce it to this way. Are we going to have a horizontal asymptote? No. Why? Because, well, first of all, it's top heavy. The degree is 2, but also because we reduced it to that. Are we going to have a slant asymptote? No, because we reduced it like that. So then what happens is we're just going to graph a plain line. However, we still need to use this denominator to exclude that x value that will cause the rational function to be undefined when it's not in reduced form. So that one still matters. So we take the x plus 1, equal it to 0 or does not equal 0. This is to find the domain. And so we can find that x cannot equal to -1. So then what's going to happen here? Well, we are going to have this thing called a hole or an open circle at that specific value. Now, how do we know? We know the x is -1. How do we find the y value? Well, we substitute it into the reduced form. So if we find -1 minus 2, if I substitute the x with this value of the exclusion from the domain, I will get -3. So that means that the point, if it was just a simple linear function, not a rational function, well, at the point, if it did exist, it will be at -1 comma -3, but it's going to be an open circle. So -1, -3, that will be, I'm going to zoom in. Okay, right there, open circle. And then what else will we have? Well, we know that the slope is 1, right? And we know the y-intercept is at 0 comma -2 because the constant term is a -2. So I can graph that one, 0, -2, and that will be a solid point because that's actually on the graph. We don't have to exclude it from our domain. And then with that said, we will just continue our line with the slope equaling 1. It will be 1 up, 1 to the right, 1 up, 1 to the right, 1 up, 1 to the right, and that will be our graph. But we cannot ignore the fact that we have an open circle right there at I want to mark it more. Right there at -1, -3 open circle, because for the domain it's all real numbers except that -1. So that's why. And we could close it here, the line. So that will be the only exclusion from the domain, and so therefore that's how it will look. Now please remember that I changed this on the problem, on the PowerPoint. This was a minus. I made it into a plus just so that I could explain why some of these graphs sometimes look like lines even though they're rational, and it contradicts everything that we learn. So that is a plus symbol. Let's make it more evident. There we go. So, and that's how it will look. Now let's just do this last problem. It is an application. We do have the answer there. So we have the example 8, the cost benefit model. So it says a utility company burns coal to generate electricity. The cost C in dollars of removing P% of the smokestack pollutants is given by the function C instead of Y, the output variable. We use C, and then instead of X, we're using P for percentage. And so the function says 80,000 P divided by 100 minus P. So it says you're a member of a state legislature considering a law that will require utility companies to remove 90% of the pollutants from their smokestack emissions. The current law requires 85% removal. How much? So this was the current, or at that moment, that is the law when this problem was made. And so they want to remove 90%. That's considering the new law. How much additional cost will the utility company incur as a result of the new law? So as you can see here, we take the function, then we substitute for every P for percentage, we substitute it with an 85. And then you could type this in your calculator, do it by hand, whatever you want. But if you type it on the calculator, make sure you include the numerator and the denominator in parentheses. And so that's what you will get. With the current law, that's the cost, $453,333. Now, with the new proposed law, you enter a 90, and you might think it's not a huge difference, but that's just how this rational functions will work sometimes. And remember how sometimes they increase without bound, so that's why the numbers, or may decrease without bound. That's why the numbers look kind of like too far apart, just for a 5% increase. And so if you type that into your calculator, you get $720,000. So to answer the question, it says how much additional cost will the utility company incur? So this is a problem about getting the difference between the two costs, the one for 85%, the one at 90%. And so that is the difference, and therefore the answer to the question. So this is the end of the video.